Welcome, ladies and gentlemen, to the live plenary track of the third day of the 21st Ifac World Congress. We will hear now the plenary presentation of Jing Sun from the University of Michigan at Ann Arbor, USA. The session chair, Hajime Asama from the University of Tokyo, will now introduce the speaker.
Good afternoon, ladies and gentlemen. Welcome this plenary talk by Professor Jing Sun. I'm Hajime Asama of the University of Tokyo, President-elect of Ifac, and the chairman of this plenary talk. It is my great pleasure to introduce the excellent speaker of this plenary talk, Professor Jing Sun. Professor Jing Sun is a Michael G. Parsons Collegiate Professor and the chair of the Naval Architecture and Marine Engineering Department at the University of Michigan. She received her PhD degree from the University of Southern California in 1989 and her Bachelor of Science and Master of Science degrees from the University of Science and Technology of China. From 1989 to 1993, she was an assistant professor in the Electrical and Computer Engineering Department, Wayne State University. She joined Ford Research Laboratory in 1993, where she worked in the Powertrain Control Systems Department. After spending almost 10 years in the industry, she came back to academia and joined the faculty of the College of Engineering at the University of Michigan in 2003. Her research interests include modeling, control, and optimization of dynamic systems with the applications to marine and automotive systems. Her current research focuses on real-time optimization and decision-making for connected and automated transportation systems. She holds 42 US patents and has published over 300 peer-reviewed journal and conference papers. She has co-authored a textbook on robust adaptive control. She is a fellow of National Academy of Inventors, IEEE, Ifac, and the Society of Naval Architects and Marine Engineers. She is a recipient of the 2003 IEEE Control System Technology Award. The title of this plenary talk is The Joy of Exploring the Emerging Dynamics of Integrated Systems. Now the artificial systems we design and realize become more and more complex, and it becomes difficult to observe the state of the systems, predict their behaviors, and control the systems. In this plenary, she will talk about her journey in pursuing the design and optimization of integrated systems, and the joy of understanding and exploiting these intriguing dynamics, which become even more essential as we seek to find robust solutions and develop enabling tools for complex control problems. Let's welcome Professor Jing Sun.
Thank you so much for the kind introduction, and hello everyone. First, I want to thank Frank and the Ifac organizers for the invitation, and also thank them for such a tremendous effort in pivoting a conference of such a scale and during such a short time to the first virtual Ifac conference. It is just remarkable. I'm extremely honored and humbled to have the opportunity here to talk about my recent work. When I was preparing this talk in the middle of the pandemic, I was looking for a technical theme that may be of broad interest and also fun and uplifting for me to prepare it. So I decided to focus on integrated systems and their emergent dynamics, especially the joy of exploring those emergent dynamics. So here goes the title, The Joy of Exploring Emergent Dynamics of Integrated Systems. The first and the most important joy in this adventure is that I had the great fortune to undertake it with a group of amazing and talented people. Indeed, the joy is multiplied when this journey is shared with those who gave me inspiration and stimulation. So I would like to start by acknowledging my students and my collaborators. I won't be able to list all the names here, so I included those who I worked with most recently and the students whose work contributed directly to what I'm going to talk about today. Many of them helped me to put this talk together, and some of them will share this stage with me in this plenary. Thinking about this talk, it reminds me of the Plenary Lecture by Peter Kokodovich almost 30 years ago, titled The Joy of Feedback. In that talk, he explained the nonlinear peaking phenomena in adaptive control and described the beautiful solutions developed to overcome that. I could vividly remember the joy of listening to the joy of feedback. Today, however, the joy that I'm going to talk about has a little bit different flavor. I'm going to focus on the class of integrated systems and discuss some of our recent work in understanding and exploring the spatial dynamics using a mixed bag of tools developed by our community, which include the design tools for feedback, feed-forward, prediction, estimation, and optimization. Let me start by defining what I mean by integrated systems. By definition, integration is an act of combining things into an integral and functioning whole. By this definition, all control systems are integrated to some extent, so integrated systems are everywhere. Well, we see them not only in engineered world, but also in social, economical, political, and biological nature systems. So here are a few examples. First, look at this. This is Michigan football. Nothing is bigger than the football game, or you call it American football game. If you are integrated into this crowd, you will feel the joy of being part of the dynamics. Here is another example. Very different dynamics. This is the Berlin Philharmonic Orchestra performing. I would have enjoyed it if we were there for Ifac. Now, fish schooling, another fascinating example of integrated biological systems. You can see the collective behavior contributed by individual fish. Finally, the transportation system. Which we all deal with every day, and it involves a lot of engineering solutions that many of us are working to improve it. Well, those examples have different levels and different forms of integration, but we see something in common. One is that the integration is driven by the collective goal of achieving better performance, and the performance could be interpreted as better efficiency, better quality of life in social, economic, or other terms, or for better resilience. Some organisms can only survive if they join force. The other is the integration, is the interactions among participating units. Those interactions can be in the form of information exchange or the contracts and the rules within the system that all members subscribe to follow. Those interactions enabled by communication and coordination define the integrated system. Here, we are mostly interested in emergent dynamics. The emergent dynamics refer to the phenomena that short-range interactions or subsystem interactions lead to high-order structure, pattern, action, or performance. Examples such as swarming, flocking for biological systems are typical emergent dynamics. In the social setting, how an organization reaches a consensus is defined by group dynamics. Of course, those are beyond the scope of today's talk and beyond my research domain. But those fascinating research activities in other professional communities, including social science, biology, and life science, can give us inspiration and stimulation. Given those general definition of integrated systems and emergent dynamics, and from those examples, we can see that following general dynamic characteristics that are of particular interest to our control engineer. Well, first, the dynamics as results of interactions and integration. Those are best illustrated by the phenomena such as synchronization of biological systems, or alignment or divergence of opinions of an organization or a community. The second is the microscopic dynamics of individual entities and macroscopic dynamics for the integrated whole, and the relationship between those two. Those are also referred to as the first and second order dynamics, respectively. Here, we're not talking about first or second order differential equation. Instead, they refer to different levels in the system hierarchical structure. For example, individual bird flapping their wing is the first order dynamic, and the formation of the group and the wake effect are the second order. The third characteristic is that those systems often involve a wide range of timescales, and timescale difference can occur at different levels of system hierarchical structure or between different and diverse entities. The fourth characteristic is the distributed nature of decision-making, especially for large-scale integrated systems, where integration merges many different entities and each may come with its own actuation. Today, I'm going to focus on the last three types of dynamics of integrated systems and discuss how we exploited those three types of dynamics as we integrate the energy system for transportation application. So here's what I intend to accomplish today, to share some interesting and intriguing dynamics that we learned. The second is to discuss how understanding of those dynamics has helped us in developing new solutions and tools. And third is to highlight some open problems and share some personal perspectives. Well, the talk will be based on our recent effort in integrating new energy and connected vehicle technology solutions for vehicle systems, including both hybrid electric vehicles and our electric ships. The relevant projects, together with sponsoring agencies and companies, are listed at the bottom of the slide. I also want to emphasize that this will not be a mathematical or theory-oriented talk. As you will see, there is a minimum set of equations. Well, neither will this be a survey talk, given that integration will touch many different topics in different domains. I won't pretend to be up to speed on major developments in all those relevant topics. So I ask for forgiveness up front, as I won't be able to list and mention all your important work. And there are just simply too many to cover. So here's the outline of today's talk. We discussed the integrated system and emergent dynamics in the general sense. Next, I will use connected and automated vehicles, or CAVs, as an example to illustrate how high-level macroscopic dynamics can guide us in control design to achieve fuel economy improvement at the vehicle level. And this is what we refer to as eco-driving. Following that, I will talk about the challenges related to multi-time scale as we attempt to integrate the power and the thermal management system for CAV, and discuss the general characteristics of the solution we propose. After that, I will briefly discuss the opportunities we explored in integrating hybrid energy storage systems and combining the complementary characteristics of ultracapacitors and batteries for all electric ship drivetrains. Then I will conclude with a few observations that may reflect my personal perspective. Connected and automated, or CAV, is a very active and dynamic research field. Many of us in this community have been working on that technology. It was initially pursued for safety and mobility, but we are interested in this technology from the angle of energy efficiency. Consider this challenge put out by US Department of Energy, the APAI program. Can we improve fuel economy by 20%? Even for highly efficient vehicles such as Toyota Prius, well, 20% is a significant number. To put that number in perspective, Americans consume about 3.4 billion barrels of motor gasoline in 2019, according to the US Energy Information Agency. So if we can save 20% of that, we're talking about almost 700 million of barrels per year. Is it possible? Or if so, how? To answer these questions, let's take a look at what is involved. Fuel consumed by a vehicle is simply the distance traveled by a vehicle and the fuel consumed per distance traveled. So it can be reduced either by driving less or driving more efficiently. The efficiency of driving is related to those terms. The first is concerned with moving a certain mass, so lightweight material and weight reduction will impact that. Well, second is related to aerodynamics. Air drag reduction is a key. So those two terms are defined by vehicle design. The other terms relate to powertrain efficiency, vehicle operation, that you have to start or stop according to the traffic condition, and driving environment. You have to go up and down according to the road grade that you're driving on. So what are the opportunities? We look into the dynamics involved in vehicle operation that may impact those terms. It includes powertrain, vehicle, and traffic system dynamics. For those of us working on powertrain systems, we know that the powertrain system dynamics have been exploited through electrification, downsizing, hybridization, and the efficiency has been improved dramatically in the last 20 years. On the vehicle dynamics, similarly, drag reduction through vehicle body optimization, adaptive cruise control, and other technologies have been developed and deployed. Then for the traffic systems, most has been focused on safety and mobility. So for each of those domains, a lot of optimization has been done and the low-hanging fruits are gone. So we believe that the opportunities are in the integration, how we integrate the powertrain system into vehicle systems and the vehicle systems into the transportation systems. This integration strategy will impact on all terms in that equation, particularly the last three terms. Now with the vehicle being connected to the network, we can capitalize the golden opportunity offered by the CAV technology. And one solution is eco-driving, and the concept we'll talk next. To illustrate the concept, well, let's think about those two vehicles approaching a synchronized intersection. And one is driven by a human driver on the top, and the other on the bottom is a connected and automated vehicle with communications to traffic infrastructure and the surrounding vehicles. In this animation, the vehicle of interest are marked by the sign color. At the start of the animation, the traffic light is red and other vehicles are queuing up in front. The human-driven vehicle stops and gets into the queuing line. The CAV, on the other hand, knows when the traffic signal will turn from red to green, and it slows down early enough so it can pass the intersection without stopping. So here are the speed profiles of those two vehicles, blue for human-driven and red for CAV. How much difference it will make? Could be 70 to 90%, depending on the assumption. I do want to point out that this is for a short distance when approaching and departing from the intersection. So a large percentage of a small number may not mean much. But if you are driving in a congested city and spending most of your time in this scenario, then the fuel saving can be very substantial. This, of course, depends on three things. First, you are connected, and your car knows more than what your naked eyes can see. Second, you can plan and optimize the vehicle speed profile. And third, the automated driving can follow any speed profile given. So ultimately, those three things could lead us to this traffic scenario. And all vehicles can drive at constant speed without stops or collisions. Well, that may be a long stretching goal before someone figures out how to make that happen. What we want to do is to understand the impact of connectivity on vehicle and traffic dynamics and take advantage of that understanding to design better vehicle operation strategies for eco-driving. Now that the vehicle can talk to surrounding vehicles through V2V and to infrastructure through V2I, how does that change the world that we're driving in? Here I'm showing a video clip from Professor Petrosiano of the University of Southern California, who is the director of the Transportation Research Center. It shows the impact of connected technology on the traffic system. This is what you see at the top. With a connected vehicle, two things have changed from the controls perspective. First, they changed dynamics in the system response. Second, which is very important to us, is that they make those dynamics more observable to the vehicle systems and the drivers. So if we understand that change in dynamics and take advantage of the observability, then we can design the control system to close the loop, as it is shown on the bottom animation. So connectivity effectively extends the driver's perception range. Well, I bet you can. To design algorithms, we need models that can capture the traffic system dynamics at the macroscopic level and connect those dynamics to the vehicle operation and energy efficiency at the microscopic level. Here, I want to mention two specific models that we exploit to achieve the 20% fuel saving target. The first is the shock wave profile model for queuing dynamics, which we used for the queuing length estimation to facilitate vehicle speed profile optimization. For a signalized intersection, this model characterizes the queuing buildup and dissipate processes with analytical expressions. It provides an estimate of the end of queuing line at the intersection. So the basic idea is illustrated as follows in the figure. The model consists of 4 different waves. The queuing wave that starts at the beginning of the red light and propagate. Then the discharge wave starts at the green light, beginning of the green light and propagate. Then the departure wave starts when the other 2 waves intersect. It pushes the end of the queuing line forward. The 4th wave, called compression wave, happens only if there is a spillover from the previous signal cycle. Those waves divide the road into 3 sections. The free flow section, where you can drive at the posted speed, saturated region, where you have to stop, and the jammed condition, where you have to drive at slower speed. So this model allows us to estimate the green light window during which our vehicle can pass the intersection. And within this window, we optimize the vehicle speed profile to avoid unnecessary acceleration and deceleration. Of course, there are many other constraints that we have to consider in this optimization. Another model that I would like to briefly mention is the driver behavior model. Those CAVs are surrounded by human-driven vehicles when the penetration rate is limited, the optimized trajectory cannot be executed if other vehicles cut in or interfere. And there has been a lot of research work on modeling human drivers. We incorporated a model that predict the time and the location of the cutting event, assuming those vehicles will send their cutting intention through V2V communication. Specifically, the notion of politeness factor and patience factor are used to characterize the aggressiveness of the driver. Those statistical models are calibrated based on the real-world data, which consists of over 100,000 lane change events. And those predictions are used to make decisions and take action to either prevent cutting or yield to allow cutting. I would like to present a case study where we apply the eco-driving strategy and those modeling tools to a hybrid electric vehicle driving near our campus. The road segment is an urban corridor in the city of Ann Arbor. It is a 3.5 kilometer stretch with 6 intersections, and it is one of the busiest stretch in Ann Arbor. The shockwave profile model is developed and calibrated using the data collected over time. And the green window is predicted based on the cooling dynamics. Then the vehicle trajectories are planned based on the vehicle dynamics, cooling length estimation, and the cutting intention prediction. Let me first show the simulation results. The basic setup of the simulation environment is the following. It is for a hybrid electric vehicle. We considered 50 scenarios when the vehicle is driving through this stretch during the rush hour between 4 p.m. and 5 p.m. Cutting events at each intersection are simulated. The results show that an average of 12% fuel saving can be achieved if we incorporate the human driver model for cutting prediction. Then an average of 13.4% fuel improvement can be achieved, as shown by the red bar in the figure. Importantly, those fuel-saving benefits are achieved without consequential penalty on mobility. In this case, it is measured by travel time. There is about 1% difference in travel time. We tested the eco-driving vehicle on the road. Our testing vehicle is a hybrid vehicle, a 2017 Toyota Prius model. The data shown here are for 20 back-to-back tests of human driving versus eco-driving. We observed an average of 14.5% fuel saving, and this is very close to the simulation result. Now I would like to introduce Dr. Yihan Feng, who I had pleasure to work with and learn from on traffic system research in general and traffic dynamic model in particular.
Thank you, Professor Sun, for the introduction. As you can see from the previous study, connectivity between vehicles and infrastructure has the potential of significantly improved energy efficiency. My main research directions are developing innovative modeling techniques, control strategies, and evaluation methods with a focus on the interactions between smart transportation infrastructure and connected and automated vehicles. Besides energy efficiency, safety and mobility of the transportation system can be greatly improved through connected vehicle technology. Toward this end, we have developed the multi-modal intelligent traffic signal systems, which utilize connected vehicle trajectory data to adaptively optimize traffic signals, grant priority to emergency vehicles, and provide protection to vulnerable road users. This system has been deployed in several locations across the US. We are also managing the world's largest connected vehicle operation environment in the city of Ann Arbor, with more than 2,500 vehicles and 70 equipped infrastructure locations. And I'm leading the data collection and analytics effort, in which a large volume of naturalistic driving data are being collected, processed, and analyzed in real time for a variety of applications.
To wrap up this section, I would like to reiterate a few points. First, connectivity changed the dynamics of the transportation system. It extends the vehicle onboard sensor and provides opportunities for closing various loops and design feedback at different levels. Understanding the dynamics at the macroscopic level leads to better vehicle operating strategy at the vehicle level. And design a good strategy requires integration of models from different domains, as I showed in the last few minutes. And then learning those models and bringing them into our feedback loop is the real joy of the integration effort. Now we move on to the next feature of integrated systems, multi-timescale. I would like to discuss it in the context of integrated power and thermal management system for CAV. Let's come back to this diagram. Consider another integration opportunity. At the powertrain level, the battery and engine integration has been investigated extensively, led by many scholars in our control community. What is less explored is the thermal and power system integration. The thermal system on the vehicle includes engine thermal and battery thermal management, as well as the vehicle cabin climate control system. So this integration is between the powertrain system and the vehicle system. With CAV, it also extends to the traffic system if we're using the previous information. The interactive dynamics between the power and thermal loop makes this problem very challenging and interesting. So we look at those dynamics. Consider the powertrain system with a hybrid electric vehicle with the engine as a primary and battery as a secondary power source. They provide the power to meet the driving demand as well as to support auxiliary systems such as informatics and climate control systems. For connected and automated vehicles, they also have to provide the power to enable perception and autonomy. The power management system has the responsibility of coordinating the power generation between engine and battery and supporting the load in the most efficient, safe, and reliable way. At the same time, the thermal management system, which controls the temperature of the engine and the battery, tries to provide the best thermal conditions for those power sources. Then there is the after-treatment system that takes care of the emission, and its performance critically depends on its thermal condition. What makes the problem more interesting here is the role of the climate control. It takes electrical power to cool the cabin in the summer, and it uses the waste heat in engine coolant to heat the cabin in winter. What is less known is that the battery system is cooled by the cabin air for a mild hybrid electric vehicle such as Toyota Prius. The cabin serves as the actuator for the battery thermal management. It makes the dynamic interaction more intricate. So let's take a closer look at the climate control system. The vehicle climate control system, also known as HVAC for heating, ventilation, and air conditioning system, has a very significant impact on vehicle fuel economy. A very comprehensive study performed by US National Renewable Energy Laboratory have shown that we spent up to 26.5 billion liters of gasoline each year on air conditioning system alone in US. For electric vehicles, the range reduction can be up to 50% if we turn on AC in hot summer days. The data we collected on our study also support that conclusion. It's not just AC, heating also takes fuel. The good news is that we see opportunities with integrated power and thermal management, especially in connection with CAV technology. As we take a deep look into the underlying physical systems, you discover that sensitivity of the HVAC system efficiency to vehicle speed that we can explore. I'm showing here a figure where fuel consumed for AC is plotted against one axis for temperature set point and another for vehicle speed. As the speed goes up and the set point goes up, AC consumes less fuel. This relates to the physics of heat transfer and aerodynamics. As ram air passes the condenser at high speed, it promotes the heat exchange rate and makes compressor and condenser more efficient. Similarly, for heating, when the vehicle is running at the high speed and the engine is running at full load, there will be abundant waste heat available. So heating is cheap. If we think of the cabin as a thermal storage, then we can have the so-called eco-cooling or eco-heating strategy. When the speed is high and AC efficiency is high, we cool the cabin a little more, just like we charge the battery. Similarly, in cold winter, when the speed is high, we heat the cabin a little bit more, so we don't have to burn fuel at the next stop to keep us warm. Well, of course, we have to do this without compromising passenger comfort. And this concept of using thermal storage to shift heat or cooling load, we call it flattening the curve. So let's take the battery-powered electric vehicle as an example. When the battery generates power, it also generates heat. And this notional plot shows the traction power in red and cooling power in blue. They both peak at the same time, and making the total power exceed the capacity. And consequently, we fail to keep the temperature within the desired region, which is important for safety and life cycle protection. However, if we have the information about the upcoming high power demand, we can pre-cool the battery and shift the cooling load so it won't peak at the same time when the traction power is peaked. The timescale separation between the power and the thermal response is a key, and multi-timescale is a blessing, as it allows the battery thermal mass to be used as the energy storage. As we mentioned at the beginning, multi-timescale is one common feature of integrated systems. The integrated power and thermal management within the traffic network is a great example to illustrate the feature. The dynamics involved are very intertwined, but they have a clear timescale separation. On one side, the engine has a time constant about 1 to 2 seconds. On the other side, the traffic system, the signal cycle is typically at order of 1 minute or so. And we have the vehicle dynamics and thermodynamics in between. The multi-timescale characteristic provide challenges as well. Intuitively, if we want to flatten the curve, we need to be able to predict the upcoming large load. If we solve this problem with model predictive control, then the prediction horizon determines whether the eco-cooling strategy is effective. And we start with 30-second prediction horizon, keep increasing the prediction horizon to 60 second, 120 second, 180 second. And we can see that the pre-cooling happens earlier and earlier. Once we get to 120 seconds or longer, we can effectively push the curve down and have the battery temperature under control. Well, the cost is a large computational footprint, as we're shown on the right. Well, this is a curse of multi-time scale, in the sense that slow time system dictates the large prediction window, and the fast dynamics define the fast sampling rate, and this combination leads to high computational demand. To summarize the problem characteristics of the integrated power and thermal management for CAV, first, the fast power and slow thermodynamics are closely coupled, and so are their constraints. For example, the battery temperature limit and its cooling capacity depends on the power delivered as well as cabin temperature control. For the subsystem involved, the dynamics of different timescale are described by different models with different fidelity. And for example, we have fairly good models for engine and battery power generation, but the models for cabin temperature dynamics are of a different nature, and they are often empirical. And when it comes to describe passenger comfort, they can be fuzzy. And we rely on having some knowledge of the upcoming load for effective power and thermal integration. And we need both short-term and long-term prediction. And those predictions will have different fidelity. Last but not least, we have limited onboard computational power and memory resources. And this is a special constraint for automotive application, especially when we expect that CAVs will add new burdens to onboard computation. And given those problem characteristics, model predictive control and hierarchical model predictive control are natural framework to address the problems involving minimizing fuel, incorporating previous information, meeting various constraints. And this is a very active research area with many experts in the audience. I had the joy of working with some of the leading researchers, and I'm handing this over to a colleague, a longtime collaborator, and a leading expert on this very subject, Professor Ilya Komnowski.
Hello, my name is Ilya Komnowski. I'm with the Department of Aerospace Engineering at the University of Michigan in Ann Arbor. My current research is in control theory for systems with constraints, including model predictive control and in control applications to aerospace and automotive systems. Besides MPC, I'm also interested in other limit protection schemes, such as reference governors, and in set theoretic techniques for dealing with constraints. Model predictive control has been very successful in terms of real industrial applications and has also been a vibrant area for theoretical research over the past several decades. Despite it being quite a mature field at this stage, I also think that some of the exciting opportunities for MPC still lie ahead, in particular in terms of addressing control problems for large-scale and integrated systems of the kind that Professor Sun has spoken about. Professor Sun and I have collaborated on several ideas in constraint and model predictive control over the years. They include robust reference governors for nonlinear systems with parameter uncertainties, parameter governance schemes, contractive MPC where contractivity constraint used to guarantee stability is imposed over a variable horizon rather than over a single time step, and an MPC strategy which exploits sensitivity-based updates called IPSQP. Our most recent collaboration has been on climate control and thermal management in hybrid electric and plug-in hybrid electric vehicles that Professor Sun has already spoken about. I would also like to use this opportunity to highlight recent work with my students at Michigan and also with other collaborators in the area of model predictive control. One of my students who has recently finished his PhD in my group, Dominic Leo McPherson, has developed the FB-STAB, which is a semi-smooth quadratic programming solver for MPC. This solver is available both in MATLAB and C++. Both versions can be downloaded from GitHub. These developments are described in our recent Automatica paper. In another Automatica paper published this year by Dominic, Professor Marco Nicotre at CU Boulder, and myself, we characterize closed-loop stability properties of systems operating with model predictive controllers that run with a fixed number of optimizer iterations per time step. Our techniques exploit the small gain theorem. Dominic, Marco, Dr. Asen Donchev, Professor Vladimir Vilov, and myself have collaborated on another paper on sensitivity-based warm starting algorithms for MPC that are based on non-smooth analysis and generalized derivatives. This paper is to appear in IEEE Transactions on Automatic Control. To conclude, I appreciate this opportunity to say a few words about some of my past and ongoing research. Thank you very much for listening.
To add to the collection of MPC tools, next I'm going to present some recent work on what we called multi-horizon MPC. For the problems that we are dealing with, we are interested in the performance of the mission, or the performance over the entire trip, when it ends and how it ends. For example, the so-called charge sustaining property requires that the charge of the battery should be the same at the beginning and at the end of the trip. So we consider the whole trip as the previous horizon and divide that into two sections, the near-term section and the long-term section. For the near-term section, we use receding horizon MPC. The model used to predict in this horizon are of high fidelity, and the information used for load prediction is relatively accurate and up-to-date. For example, we use V2V communication. The model is updated with a fast sampling rate to capture the fast dynamics. For the long term, shrinking horizon is used, which gives us an estimate of the cost to go for the integrated optimization problem. In this horizon, different models have to be used. Decision will be made based on the information that's available. For example, the traffic history data has to be leveraged for predicting the long-term power load. The sampling rate is set as relatively slow to manage the computational demand. At the beginning of the trip, the long-term prediction may be rough and uncertainties are large. As the time proceeds, the receding horizon moves forward, the shrinking horizon compresses. At the same time, the predicted load profile gets updated and its uncertainties are reduced as we get closer and closer to the end of the trip. Now we apply the concept to the problem that we start with, to integrate the power and thermal management system for connected and automated vehicle. The system involved is notionally illustrated here. Note that the engine is the main heating and power source. For the cabin, the heating energy is stored in the engine coolant and delivered to the cabin through the heat core. The scenario that I'm going to focus is in cold winter day with a high cabin heat demand. The goal is to minimize fuel consumption while enforcing the constraints. The system includes 3 states, one for energy storage, that is the state of charge of the battery, and 2 for thermal storage, the engine coolant temperature and cabin temperature. Those 3 states are closely coupled. To apply the eco-heating concept we discussed earlier, we formulated the problem and designated the cabin heating as input rather than a response variable. It allows us to manipulate the cabin temperature within the constraint set to achieve the optimal fuel efficiency. We applied the multi-horizon MPC to our model. First, we consider the baseline performance, where the conventional MPC with receding horizon is designed. The cost function is the fuel. The second term is added to put a penalty on the final state deviation for the battery state of charge. As an example, we apply this to New York City drive cycle, which has a lot of start and stop. And here's the result. The blue bar on the slide is the result of dynamic programming, which is the ultimate optimal solution if you know the whole drive cycle. And we use it as the benchmark to evaluate the performance of other MPC. As you can see, with 20-second prediction window, we lost about 5% of fuel economy performance. We can extend the prediction window to get some of the lost performance back, but with a steep penalty on computational cost. For the multi-horizon MPC, we have the same problem formulation and cost function, except that instead of penalty on the terminal condition at the end of the receding horizon, we have an economic cost function for the rest of the trip over the shrinking horizon. We use the 20 seconds for the receding horizon, and the total trip was over 500 seconds. Note that in terms of the fuel consumption, the multi-horizon MPC, shown here in green, will get us very close to that of the DP result. In terms of computation, it is slightly increased compared to the conventional MPC with 20-second receding horizon, but much less than other MPC strategies with longer receding horizon. We also tested the multi-horizon MPC for eco-heating on the vehicle. As we have different ambient and road conditions, we saw an average of 4.7% improvement. And this improvement is much more pronounced for cold ambient condition than for relatively mild winter condition. As you see through this case study, the power thermal coupling presents an interesting example and motivated us to develop new tools for effective integration. But I'm sure you have noticed we have a lot of questions unanswered, both on the theoretical front and on implementation aspect. For example, what are the properties of multi-horizon MPC? Can we guarantee feasibility at each step? How we do long-term predictions? How do we deal with uncertainties? The good news is that those open questions provide opportunities. So we'll continue to have the joy of working with colleagues to tackle them. With that, I would like to present my colleague and my long-term collaborator, Dr. Julie Buckland-Seed.
Professor Sun, Professor Kolmanowski have highlighted some of the exciting opportunities that come from integrating dynamic systems. The fun really begins, however, when we consider implementing these concepts in a large scale in real-world scenarios. With this implementation comes many challenges, for example, computational demand. But the challenge I find most intriguing is the uncertainty we find in the preview information that we're using to make control decisions. Now, it's difficult to accurately predict the future in general, but it becomes extraordinarily difficult when we consider the emerging dynamics of integrated systems. For example, consider a family of ducks crossing the road. This is an example of the duck transportation system interacting with the vehicle transportation system. And it's only one of many examples I can come up with where there's an interacting system that disrupts traffic flow. So an important question is, how do we make the benefits of connectivity robust to uncertainties like this? And that's the question I want to leave you with, because it's an important question that must be answered if we're going to realize the benefits of this technology in our daily lives. Thank you.
I would like to wrap up this topic on multi-timescale with the following remarks. First, it is important to take advantage of the dynamic interactions of thermal and power system to be able to achieve what I refer to as 1 + 1 greater than 2. In this case study, with eco-heating and eco-cooling, we achieved more than what normal thermal and power management could achieve. Second, multi-timescale is a double-edged sword. We took advantage of it for eco-heating and eco-cooling, but have to manage the computational burden. We developed a new framework for multi-horizon MPC, which allows us to leverage different models for prediction and optimization, and achieve good trade-off between performance and computational complexity. From both modeling and implementation perspective, there are many open questions and interesting problems that will keep us motivated to seek new tools and solutions. Before I move on to the last segment of my presentation, I would like to circle back to the million-dollar question we had before. Can we achieve 20% fuel economy improvement, even for fuel-efficient vehicles? We presented some solutions that cannot be categorized into the conventional powertrain or vehicle or traffic system domain, but they belong to the intersections. I believe it is possible if we take the integrated approach, as well as taking full advantage of the connected and automated technology. I hope you also feel as hopeful as I do. Now we move on to the final topic. I would like to use the hybrid energy storage system to illustrate the important feature of integrated system that's related to the multitude of control actuations and what we do or not to do with them. Oftentimes, integration involves bringing together multiple systems with complementary characteristics. This can be best illustrated with a hybrid energy storage system. Consider different storage options for vehicles and ships. We have capacitors, batteries, and flywheels, for example, and their energy and power densities are illustrated in the so-called Ragan chart. If you compare the battery and ultracapacitors, batteries have high energy density but low power density. The ultracapacitors are the other way around. So there's no clear winner when you compare them on those important performance attributes. But if we combine them, we will have a hybrid energy storage system and can have the best of both. For that reason, the hybrid energy storage system have found applications for HEV and all-electric ships. Well, let's talk about the hybrid energy storage for all-electric ship drivetrain. Well, compared to ground vehicle electrification, ship electrification has perhaps made less headlines in the last 20 years. But there have been a lot of technology advancements in this area. All-electric ships, or we call it AES, are the most significant results of ship electrification. AES refers to the ship where all the power on board the ship is generated and distributed in an electrical form. It is one of the fastest growing segments for both commercial and military ships. For the conventional mechanical driven system, the ship propulsion system and the ship service loads are powered by separate prime movers. For all electric ships, those two systems are integrated to form a single onboard power microgrid through the so-called Integrated Power System, or IPS. IPS is the most comprehensive integrated system that I have worked with in the past 15 years. All the dynamic phenomena, such as multi-time scale, complementary and redundant actuations, microscopic and macroscopic dynamic responses and interactions, all have their manifestations in IPS. Well, for today, I want to zoom in on just one special aspect of this key technology, which is the integration of HESS. HESS, or Hybrid Energy Storage System, is used in IPS to increase efficiency and reliability of shipboard power microgrid. Well, let's look at one specific application, which is to reduce the drivetrain fluctuation for the propulsion system. As the ship is moving through water, especially in rough seas, the load seen by the propeller fluctuates as the propeller rotates in and out of water and pierces through waves. Well, this figure shows the largely varying thrust measured. Most of the fluctuations can be attributed to propeller's rotating motion and wave encounters. They have distinct frequency characteristics: high frequency for propeller rotating motion and a low frequency that corresponds to wave excitation. So if we match those load characteristics with the device performance of the hybrid energy storage, naturally we will have the battery to take care of the low frequency load variation and ultracapacitors to deal with the high frequency fluctuation. But this combination does not lead to expected result. What you see here is the result of three different systems, one with ultracapacitors only, that's the blue curve, the other two with hybrid energy storage with different integration strategy. One axis reflects efficiency measured by energy loss, another reflects the tracking performance measured by tracking error. For all cases, model predictive control is used to design controller. The results are shown for two different C states, C state 4 and C state 6. Well, we can see that the purple colored curve, which is a hybrid energy storage integrated with the strategy we just mentioned, have worse performance than a single type energy storage. So for synergistic integration, we took the approach that encompasses the full cycle of understanding the physics. In this case, it includes the hydrodynamics and the propulsion drivetrain system responses, and developing optimization-oriented model with the proper parameterization. We also invested in the optimization algorithm that can take advantage of the component and the system characteristic explicitly, as briefly mentioned by Professor Ilya Kolmogorov. The final element in this cycle is the testbed that allows us to implement real-time optimization and validate the result. At this time, I would like to introduce my collaborator, Professor Heath Hoffman and Dr. Jing Sun, to walk us through our integration testbed.
Hi, I'm Heath Hoffman, a professor in electrical and computer engineering at the University of Michigan. I specialize in power electronics, electromechanical systems, and energy storage. My entire career, I've been fascinated with the integration of the rational and the empirical. To that end, I very much enjoyed working with Professor Soot in the implementation of advanced control techniques in the Michigan Power and Energy Laboratory, with the goal of dramatically reducing the greenhouse gas emissions produced by vehicles. As one example of this work, our assistant research scientist, Jing Sun, will briefly discuss his contributions in the area of hybrid energy storage systems.
Hello everyone, this is Jing Sun. I'm happy to give you a virtual lab tour here at the University of Michigan. What is behind me is our testbed, including the hybrid energy storage system. So we have the supercapacitor pack, we have the battery pack, and also we have flywheel. Different energy storage has different characteristics in terms of the power density and also energy density, so they can complement each other. By leveraging the emergent dynamics of this integrated system, we optimize the sizes of different storage and also the power management strategy at the same time to realize their potential abilities in a proper way.
To wrap up this section, integration is about finding synergy. So we show a simple example where intuitive strategy, even with MPC, can run into the situation of 1 + 1 less than 1. And this is what we want to avoid. Hybrid energy storage and integrated power system exemplified the nature of most integration effort. And the joy will be in integrating different modeling, optimization, and experimental tools. In the presence of those redundant and complementary control actuation is another special feature of integrated systems. Calling it over-actuation may be misleading. This is an opportunity for us to take advantage and leverage those additional degree of freedom to address other objectives, such as condition monitoring. And this calls for new design and computational framework. Now we come to the conclusion. After you have seen those case studies and heard a few of us talking, I hope a theme has been emerged and you see this as an integrated talk. To end, I would like to offer a few remarks as a final thought. First, integrated systems with rich dynamics are control intensive. And the modeling is more important than ever, in my opinion. And so is data. With the rapid development in artificial intelligence and machine learning, we have new tools to help us. But those tools are meant to augment, expand, and enrich our tool set, not to replace the understanding or displace what we have developed in the past 50 years. For integration, managing the multi-time scale is one key. and striking a good balance between efficiency and resilience is another. And I see plenty of opportunities to develop new tools and frameworks. I also want to note that integration is a team sport. Interacting with domain experts and learning from them will be a lot of fun. Well, I once heard this expression from a friend, close your eyes, linearize. Of course, this is not what we do. So I would like to end with this expression, open our eyes and explore dynamics. With that, thank you all for your time and attention. I look forward to interacting with you offline or in the live session at Ifac.